Hello, everyone.
Hi, good morning. Rich, if you guys are ready, maybe we can just start the weekday. I understand people have work issues.
Yeah, okay. Could you let me share my screen,
Oh,
please?
yes. Since it's recorded, so we are good.
Okay, I'll run through what we're going to do. We're going to run through exactly what we've done and what our findings were. Manasseh and Roy were working together, I think it was last night, and on their deployments, and there was a couple of issues with the deployment. That they couldn't trace it back. They spent about 2 hours on it, so we are unable to give any information on that at the moment. But what I can talk about what I've done, and Manasseh can talk about her artificial neural network, and Michael has also got some fantastic work that he can discuss as well. I'll go first, and then I'll hand over to Manasseh, and then she can hand over to Michael. Manasseh, Michael, does that sound good to you?
Sure, Rich, yes.
Yeah.
Sounds great.
Cool. Okay, so the first model I used was XGBoost, and I'm going to go over a bit about what XGBoost is. It's very powerful, but I thought rather than jumping in straight to our results, it might be nice to just give a bit of information around what it is and what it's for. So XGBoost stands for an extreme gradient boosting tree, and a gradient boosting tree is basically a decision tree ensemble learning approach, and it's used for classification and it's used for regression as well as feature selection. It's very, very similar to a random forest. And so what happens is there's multiple machine learning algorithms are combined into an ensemble, and the aim of this is to produce a better model. It's got more predictors, it's got more sort of computation trying to work out the predictions at the end, basically. So what the extreme gradient boosting tree, it's made of numerous decision trees, and the only difference between a normal random forest and an XG sort of gradient boosted tree is that in terms of how the forest is constructed, and I'll get into that a little bit later on. So let's just go to the next slide. That is definitely not the slide I wanted. Or is it? Yeah, it is actually. Never mind. So what sort of I'm going to talk about how XGBoost works, and basically the premise of it, it's a method called bagging, and what that basically means is that the number of individual decision trees are used concurrently, and they use a random forest certainly uses a random bootstrap samples of the data, and how it makes a prediction is that it averages all the decision tree forecasts to give you a final forecast. The term gradient boosting in this particular context basically means that it boosts or at least strengthens the weakest models by fusing that particular model with other weaker models in the selection, and hope the purposes of that is to make the model more robust. It basically it reduces errors, so each iteration uses the previous what's it called, the previous residual error, and fits it to the next tree, if you know what I mean. So simply, a group of shallow decision trees are trained by a gradient boosting decision tree, and on each iteration the error residuals of the previous model is fit to the new model, and then the weighted average of all these predictions presents the final prediction. So that's what it means by gradient boosting. So XGBoost is an extreme example of that. It's scalable. It's extremely accurate. It pushes the limits of the computational power, and it was generally created to enhance performance and the speed of machine learning models. And how it does that is that instead of the random forest trees are built sequentially, where the ones in XGBoost are made in parallel, which significantly increases the speed it operates at. So that's basically how that works and XGBoost works. So the next slide is the model details. So these are the results I got from my XGBoost experiments. The baseline model, we used the MAE metric, and that was 0.456. And what I done was the first instance here, the optimum parameters for the grid search. That actually made it a lot worse. Well, not a lot worse, but a little bit. No, it actually improved it. 453 was the MAE. However, Diane raised a good point about interpretability, and because I followed the LGBM pipeline, the target variable was transformed. This means that my output metrics are also transformed, so they're a bit more difficult to interpret. So what I've done was I've actually calculated the MAPE, or the mean absolute percentage error of these, and I'll show you what I've done there in the sort of summary of my models. Moving on to the randomized search, I increased the amount of hyperparameters that are tuned, but it didn't really work very well. As you can see, it went to 476. And the R2 number went down and the RSE went up. So basically, the third randomized search I done, I tightened up the hyperparameters because I thought that maybe I was giving it too many options. So I tightened up the hyperparameters and it improved the score. So let me just load up my XGBoost. So there we go. Okay, so the MAE is 4.47, and that gives us a MAPE of, give me 1 second, of 4%. So as you can see here, it's 4%. So what that means is the prediction is around 4% incorrect from a true value, which isn't too bad. You know, I thought it was going to be quite a lot more, but I was actually surprised that it's only 4% off. I'm currently calculating it for the random forest version, which I'm going to go on to now. So these are the param searches that I used. The first one being the grid search. You know, I looked at the minimum child weight, the gamma, the subsample, just a random selection really based on the default settings. The second one, I went into a little bit more detail with them and how it actually ran through them. So see, I've actually got a loop in between certain values at points of 10. That it took a long time to run, probably about an hour and a half, but it didn't really do that much to it. It was only when I then went to the third one and refined it a little bit more, give it less choice, basically, that it went. It actually increased the MAE, and you know, obviously got the MAPE of 4%. The next part of it, I tried the random forest. Now the random forest, I'm not going, you know, it's very similar to XGBoost. I'm not going to go into it too much. I don't want to, you know, reinvent the wheel or teach it how to suck eggs. But basically, a random forest supervised learning algorithm. It's a group of decision trees. It uses the Baggin approach, where it takes the best it takes the average of all the predictions and gives you a final output. So there is a benefit of using random forests, given, you know, if you use it in classification and regression. A lot of machine learning problems are classification or regression, and random forest can be used for them. It's like a massive if-else statement, quite powerful, and it does get good results. It is always a good algorithm to start off with. Okay, so what I did there, let me just change the slides. Okay. It's lagging behind me. Laptop's really slow today for some reason. I only done 2 hyperparameter searches on this. That was only because me computational power, it was taking quite a significant amount of time to run, and I run them through my work laptop, so I needed to go back to work a couple of times. So it's just one of them. I just couldn't do it. And we got pretty good results. In fact, the second result on the randomized search was actually better than the the XGBoost, which I was quite surprised at, but there we have it. And again, I used a param grader, quite a simple one, in the first iteration. Didn't do too well. It didn't get much above the baseline, so not much improvement. So the second one, I tried something else again, and I used the NumPy linspace. And I started, like, for the first one, the N estimators, the amount of trees basically is, I started at 100 and it stopped at 200, and the number was 10, so it done it in sort of grades of 10. And I also done that for the max depth as well, between 2 and 20. So that one basically got the highest score for the random forest. I'm still trying to calculate the MAPE for that, but the baseline model got 3.8%, which, you know, isn't too bad. It's actually better than the hypertuned XGBoost. It's still running at the moment to try and get me a better MAPE for the second one, because I only thought about doing this today just for ease of interpretability. So I'll let you know what that MAPE was on the second run for this particular set of hyperparameters. And then these are the results that I got in table format. The MAPE for XGBoost was 4%. So if you unscale the target variable and it predicts a certain value, it shouldn't be, on average, it shouldn't be more than 4% of the way of the true value, which I'm quite happy with. And the random forest, I imagine it's going to be around the same, or if not, you know, a little bit more, just because the MA is a bit better. But I'll fill that out once I get the results after it's run. It's been running for about an hour at the moment, so, you know, stay tuned for that one. And that's pretty much me on that term. Manasseh, do you want to share your screen and go through your part?
Yes, Rich, sure. Let me do that.
We'll take questions at the end. Just let everyone run through their bits and bobs just to save a bit of time, and then we can have a discussion at the end. Okay, I'll stop sharing my screen. Manasseh, the floor is yours.
Yep, thanks, Rich. So do you guys see my screen?
Yes.
Yeah. So to start off with artificial neural networks, so we need to understand like where the artificial neural network got originated from initially. So we need to understand the basic neuron model, or a biological neuron model. So where so this is, I mean, the entire neural network's logic was taken from this particular thing. So you can see that. So these are the dendrites. So they act as a means or a channel where it collects the signals and it sends it to the neuron. So you might be familiar with neuron or cell biology, right? So neuron will have a nucleus. It will process all the signals and it will send the output across the axon. So this was the basics behind like how artificial neural networks or neural networks was originated. So if you so the single neuron artificial neural network is also called as single layer perceptron. So here what happens is you will have input features that will, along with the weights and bias, it will be fed into the neuron. So this is a single neuron which will have an activation function. So it will process all these weights and the input features along with bias, and it will create an output. So this is the formula, which is, I mean, this is the math formula which is used. So this is simpler. So if you have come across the regression formula or other formulas, you can see f of xw plus bias. So that is how the prediction of your output is done. So when you see an example of math behind this particular artificial neural network single layer perceptron, so you can see like there are like inputs that is being fed. So these are the examples of like what input is being fed. So 1, 3, 4 are your input. So that is like fed with a weight. So each and everything will have a weight associated with each and every feature that will be multiplied with that weight, and then you will multiply. I mean, the bias here is 0. So usually the bias can be like a little bit greater than 0 as well. So it would be like basically between 0 and 1. Even the weights as well, it will be between the values of 0 and 1. So you will compute your output, and then once you compute your output, you will compare your actual y value with your predicted value. So then you'll compute the loss, and then again you'll go back and retrain your model by updating the weights. So the process from input layer to the output layer, propagating from left to right, is something called forward propagation. So here it is like you feed the input to the neuron, then you compute the output. So that process is called forward propagation. Again, when you go back and update your weights, once you compute your loss, you update your weights based on the loss that you have got. That is done using something called derivative chain rule. So again, that is mathematics behind artificial neural networks, which is hard for me to explain right now. But I have put some links links as notes in every particular slide. You can go back and check those links in order to understand the in-depth mathematics behind this. So once you go back and update your weights, that is called backward propagation, where you will find the derivative of rules and stuff like that, and you will compute everything, and you will redo the weights, and then again you will do the forward propagation. So this one complete iteration is called damn, I forgot the word. Okay, epoch. It's called one epoch. So one forward propagation and one backward propagation together is called an epoch. So here your activation function can be anything. So they usually use sigmoid activation function. They use ReLU as an activation function. So I'm not going to go in depth in that. So this is like a basic math behind how a single layer perceptron works. Yeah. So in our case, so the artificial neural network. So in our case, we have used multi-layer perceptron. So multi-layer perceptron. So in single layer, as you saw this, so you have a single neuron, right? So that's why it's called single layer perceptron. But in multi-layer perceptron, what you can see is you will have multiple neurons as different layers. So here you can see two hidden layers. So all these are neurons, and this is the input layer, and this is the output layer. So you can use like multiple neurons. So you can also like deactivate the neurons in the hidden layer. So I'll go to that when I explain the code. Yeah, so the ANN model didn't work well with our data. So these are the metrics we found. So what I did was, so I took raw data initially and did some basic computation, like basic pre-processing of the data. And I directly passed that data into our artificial neural network model. And this is the metrics that was obtained. So similarly, so I took whatever feature engineer data that Rich or Salman had done. So I just directly passed those, and it is similar to KNN imputed and simple imputed as well. So let me open up the code itself. The code. Yeah. So initially, so ANN on raw data. So I picked up the raw file and I did some pre-processing where I removed all the, I filled all the null values with the mean values for all these for days with fog and energy star rating. Then I converted all those, what was it? Yeah, so again, like y raw, so again I read the raw file for the y trained raw. Then I did one hot encoder for all these categorical variables. Then I did I scaled the features for both x and y trained data, like x trained data and y trained data, both for test and train. And then I passed it. So I actually used TensorFlow Keras for ANN model. So it's a sequential model, and when you see the dense, so 500 neurons initially, which was used. So you have to pass your input dimension. So in our in our raw data set, we had around like 46 input dimensions, and I used the kernel initialization as normal. This is the basic configuration we usually use, and I used activation function as the ReLU activation function. Then, so why I've used dropouts is, so that's what I was talking about earlier. So you can actually deactivate like 0.3% of your hidden layer neurons. So you can deactivate them. So you can connect only like rest of the neurons to the next layer. So that will actually help like in overfitting. So it will reduce overfitting. So that's the reason they use like dropout as a feature, or I mean dropout as a process for like deactivating your neurons. So here I'm using like 3 hidden layers, and the final output layer with activation function as linear. So it will, so based on your layers, it will calculate like what is your total parameters and trainable parameters and stuff like this. So these are the metrics of what your sequential model would look like. And once you compile your model, so I'm using loss as mean square error, and I'm like just fitting the model now. So why I'm using early stopping is, so what happens is like usually artificial neural network usually takes a lot of time to execute. So in order to see like in order to stop at a point, like at a threshold point, you can use early stopping. So what I have done is, so it will, so the patience, if you set it to some value, whatever you want. So I have set the patience to be 5 here. So what happens is, once it stop improving the values, like loss improvements here, like if once it stops reducing, once the values get constant, so for around 5 iterations, then it will stop training the module, or stop training your model. So here it stopped at 13, right? So you have given your epochs as 20, but it stopped at 13. Because if you go back like 5 before, whatever, from 13 to like the 5 before of that, you can see it stopped improving the model. So that's the reason I've used early stopping, so that, so once that threshold is reached, it, whatever, like it stopped improving, it will stop running the model. And the similar way, like I've plotted the graph for training and validation losses, and it's the same for scale data as well. So I've used similar kind of configuration, with just the dimensions would be different. So for feature engineer scale data, that dimension was around 69 features. I've used a similar configuration to calculate all of them. So artificial neural network model didn't perform well. So it performed well on raw, I mean, like better than others on the raw data. When you compare the KNN imputed, simple imputed, and feature engineering data. So it performed better on raw data. So this is not a model that is good for our data set. That was the inference we found. Yep. Then I'll hand over to Mike. So this is what I was talking about. So so you can see the image source and also GitHub link and some of the links which explains you about mathematical intuition behind the single layer perceptron or artificial neural network basics.
I'd just like to add as well, just before Michael starts, since the Manasseh's model didn't work too well, it allowed us to do a little bit of research though to why. And neural networks with tabular data don't really go hand in hand, because just the way that the data is stored, basically, and it's difficult for a deep learning network to exploit some of the features in the data, because it's not very dense, it's not very continuous and whatnot. But Google come up with a model called TabNet, and I believe it was released in 2019, and it's a neural network that's specifically used for tabular data. And apparently, when it's being benchmarked, it does perform better than tree-based models. I haven't implemented implemented it, but it was something that I wasn't aware of before. I'd never heard of it before, because I always thought, a neural network on tabular data, we won't really need to use it, kind of thing. But apparently it's really powerful. It doesn't need any sort of pre-processing of the data before you put it in, and it picks up its own features and whatnot. So I would suggest taking a look at it if you're interested in neural networks, definitely. And I will definitely be the good thing is Manasseh, we learned a lot from Manasseh's model, because it didn't go as planned. So yeah, it was, it's disappointing that it didn't work, but it was a learning experience, and I've come across TabNet, which I never would have even thought of before this happened. So yeah, definitely worth looking into. Michael, all yours.
One thing to ask Vanessa before Mike takes over, and I agree with Rich completely on. Yeah, the whole idea is as a learning experience as well. The TabNet thing, if at all, her results made me more excited to see how the TabNet works with this. Vanessa, one quick question.
Sure, man.
Yeah. Where did you, on once you put data and all that stuff, where did you get the input dimensions? From where were you picking that number? Initially, it was 40 something.
Yeah. The input dimension is the number of features in your input.
Oh, that's what you're referring
to. Yes.
But it was 44?
46.
46. Okay, yeah, I guess. Do you mind going to the slide? Maybe
sure.
Part, I guess.
Yeah, sure.
It was categories combined, removing some features. That's why it might have.
So I guess it depends on the data she picked.
Yeah. So if you if you see the shape, like 46. So that is your number of features.
Okay, that's
right?
a refined transform data. Sorry.
Yes.
Okay, got it. Thank you.
So this is the this is the columns, and this is the one. So the input dimension will be your column.
Right? Yep, makes sense.
Yeah.
Yes, thank you.
Thanks, Emma.
Right. Any other questions, anyone, before we move on? Pass it down to Mike. Okay, I guess I assume we are good. Okay, go ahead, Mike.
Okay, 1 second. Okay, so everyone can see the screen sharing is working?
Yes.
Okay. So working with Rich and the rest of the team, I decided to take a slightly different approach to the actual feature selection and data considerations, thinking about this project from a more understanding what's going on type of view. I looked a little bit more deeply at like what Energy Star rating and site energy usage were, and the degree heating and cooling days. And I kind of, I have my actual background is in building and facility maintenance. So this is in many ways, a lot of this is kind of in, I have domain knowledge specific to this. So, I mean, Energy Star rating is just a relative performance metric. Is from 0 to 100, and it's just based on how your building ranks in energy usage against all other buildings in the same category as yours. So by determining what your Energy Star rating is, it gives you a lot of insight into how much energy you're actually using, and in many ways for a climate based idea, like you might think that just selecting upon Energy Star rating would probably be one of the best ways to do things, because it shows you where you probably have, like, buildings with low Energy Star ratings are going to have more distance that they can improve their efficiency essentially. Site energy usage is also a relatively simple metric in that it is just the amount of energy used for a given gross area of a building. So which is generally just, it's calculated as a gross energy usage, which is just, total amount of BTUs for whatever which is converted from electricity and everything else. And then the heating and cooling degree days were one of the other features that we looked at, and that is just essentially the sum of the difference between the average daily temperature and 65 degrees, either positive or negative. So it's the sum of the absolute values of that. So like your cooling degree days are the total amount of time you're spending below 65 degrees, and your heating degree days are the total amount you're spending on average above 65 degrees. So thinking about that, I eliminated most of the highs and lows and averages because that information is all contained within heating and cooling degree days. You know, and looking at the fact that Energy Star rating tells us essentially what our site energy intensity usage is going to be based on our heating and cooling days, that makes that like kind of the most important thing to get right. And we have a lot of missing Energy Star ratings, which is not actually that strange of a thing because it's actually a whole process to get your building Energy Star rated. So our ability to effectively impute Energy Star rating is probably one of the most effective features that we could work towards. Thinking all this, I limited all the feature selection down to this feature selection I have here: state, facility, floor area, Energy Star rating, cooling and heating degree days, site EUI, which is our target variable, and then age. On just some preliminary running this through a random forest regressor, it was the most effective. I was able to get an root mean squared error of 0.54 using a scaled version of the site EUI, similar to what Rich did, or 28.9, which is the non-scaled version, of the actual target variable. So looking at site EUI as the actual number itself, which to be honest, I think are relatively, Rich was talking earlier about, the percentage error, essentially, like looking at how much off each individual estimation is. And I think that from my perspective, the percentage, as long as it's relatively low, you don't need to be spot on, because we're just looking to understand what the ballpark energy usage is for determining whether or not this building should be looked at for, in my mind, looked at for renovation or energy efficiency upgrades. A difference of 3 to 5% is insignificant when you're talking about the total energy usage of a building in itself, particularly for buildings where you might be able to increase your energy efficiency by 30 to 50%. So after doing the initial run through of the random forest model, Rich and our team talked about possibly evaluating how we were doing the imputation. Looking at Energy Star was kind of our most important thing. Getting the data right for imputing those values had the greatest impact on model performance. So I ran some tests on the KNN imputer, changing the number of neighbors and some of the other hyperparameters for just the KNN imputer. It turns out that between 4 and 6 neighbors performed relatively equally well, but outside of that window, the performance dropped off significantly to the point where the model was not necessarily performing poorly, but performing intermittently. If you running it multiple times, you would end up with kind of widely variable returns from the model, which are not always is kind of a sign that things are starting to move in the wrong direction. And as you got further away from that window, it got even worse to the point where the model was fundamentally unusable. I think one of the reasons this probably is that because in the data we have 6 years of various representations of buildings, I think that the KNN imputer is lightly picking up on that presence and is seeing that these are groupings that it can identify, and it's in some ways probably picking up that information out, which is why having larger numbers of neighbors is not improving the performance with any significance. I then ran a couple of different random search CVs to try and pick out better groups of hyperparameters for the actual model itself. I ran through this a couple of different times with several different sets of parameters. None of them ever turned up a significant performance increase. Most of them, most of the best models that were returned were either worse or fundamentally the same. Even I've tried cutting down the number of parameters that were being searched a little bit as well, pruning things down a little bit, and that didn't seem to improve performance either. Although it did speed up the actual search. After I kind of felt like I had exhausted the hyperparameter tuning, I decided to take a look at maybe expanding the use of our KNN imputer. And what I found was that we can leave all of the data in. So in most of the data sets that we've been using, people have been removing the outlier or the NaN values from building age slash building build year. And what I found was that we can use the KNN imputer to also impute those age values and keep that data in. I was able to rerun all of using every single sample in the data set. I was able to rerun these with a very minimal impact on model performance. We lost about 0.25% explained variance and 1 or 0.42042 RMSE. So I think that this works very well for this data set, because I think, from my perspective, at the very least, I think that this covers a very important part, which is that if I'm looking at trying to identify buildings that are, if I'm looking at buildings that need to be updated, I would like to be able to put in essentially the most generic and generalized data that I possibly can and get some relatively accurate answer out, rather than, cutting down and pruning what we're able to input into the model, even if we're able to gain additional accuracy. And like I said before, my reasoning behind this is that I don't know that gain in accuracy is going to have a significant impact on someone who is making a decision about whether or not this building should be, renovated or updated. A 5% or a 2% improvement on accuracy of the model, I don't think is going to change the difference between whether or not you're going to decide to renovate this building or not. But being able to put in any building that we have data for and get some sort of reasonably accurate answer out, I think is more towards solving the problem of where do we start, what do we need to do for this. So that's kind of where we ended up. The meeting is just about to end, so we can maybe all leave and come back, and then we can answer any questions.
Yeah, let's rejoin it in case somebody has questions, and then we'll wrap up. I've given you access, Mike. Okay.
Okay, wonderful. So this final, hold on, what is going on? This last matrix is, this includes the data that believe Rich put in earlier, and myself, kind of comparing the various performances of the models that we put together as a group. I think that we have come up with a couple of different models that at the very least are providing sufficiently accurate information to answer were this to go to a client, which I think is the important piece, is like, are we answering the question as to which buildings should be looked at? And I think that we can resoundingly say across many of our models that yes, we can provide data that would lead to actionable responses, essentially. But does anyone have any questions about my approach or comments?
Any questions, anyone? Now's your time.
We've got two other. We need to do the deployment, and Nuktar has done a time series operation, but nothing. She obviously can't come to this meeting just because she's got work commitments, but she will present them, and hopefully we can present the deployment aspect of our team later on. Maybe next week or Sunday or whatnot. But that's all the thing. That's everything we're missing at the moment, because we did have a couple of difficulties. But yeah, if there's any questions about anything that we've seen today, just please speak up or send us a message.
Any questions, anyone? Well,
We must have explained it really well then.
Well, good job in making those slides, and feel free to everyone just watch these recordings if needed, maybe on Sunday when they deploy or show other stuff, so then you can ask those follow-up questions somebody has. And Komal, would be great, questions to lead as well, like if you guys can post, Komal, have you created that file, so at least where they can post these stuff, that will be helpful, so at least we can compile.
Yeah, so I had a doubt, Imran, regarding the same. I posted you also. So can you just give a quick idea on what exactly they have to mention in the summary Excel? Is it the approach that they took and the models that they used and final model that they selected? Is it like a kind of a bullet points in terms of theory that they have to summarize?
Yeah, a few bullet points on what they covered. They don't have to say why they covered, just what they covered, that's it, because it's a high level one. So then we have a whole comprehensive report on what we covered in entire project in terms of different teams. So
Okay,
that's a high level one, that's it. So they can just post whatever techniques they covered, like ANN and then random forest and all.
Yeah.
Yes, exactly. So that's just a high level, few bullet points, maybe 4 or 5 bullet points should be enough, I guess, per team.
Okay, so
So that
I'm
should-
gonna share. Yeah, I'm gonna share it right after the meeting, and then leads can start putting their data.
Yes, that'll be helpful,
Yeah.
Rich and his team, if they can get it done by Sunday. So at least we have a record of these two.
Yeah, sure.
Yep.
Okay. Thanks, guys. If nobody has any question, then we will meet on Sunday at 9 a.m. Eastern time.
Sorry, Imran, I have a
Perfect.
question.
Yes.
Unfortunately, I made my model, but I couldn't put it in the PowerPoint because I'm sick for 1 week. I just came to the meeting because I promised my group, even it's hard for me to talk. So do you want me to
That's
copy
nice
and
of you.
paste what I made in the PowerPoint now? I present it later.
Yeah, Masood, you can do that. You can add it in our section, and then if you feel better on Sunday, you can present it.
Oh,
Yes,
great.
that looks more logical. Yes.
Created 4 model, but sorry, guys, it's really even hard for me to talk now.
No.
No,
We don't
please
want you
say.
to do that. No.
Yeah.
Thanks
Thank
for
you.
at least. That's
Yeah.
very nice of you. At least just keep us updated and coming in. No, just keep it that for Sunday. But yes, PowerPoint will be needed. Otherwise, participants won't be able to keep up anyways. So okay, let's shoot for that on Sunday as well. And whatever the left part which Rich wants to cover as well, let's do that. I hope. Yes, let's do that. Okay, guys, have a good day. I'll see you guys on Sunday.
Yep. Thanks very much,
Everyone,
everyone.
thank
See you
you.
on
Thank you
Sunday.
very much. Thanks.
bye.
Thanks, everyone.
Bye-bye.
Thank you. Bye.